Well,
yeah. I mean, I think we've all been there. Many of us have. So we're going to enter the real world here. And by virtue of that, it's my pleasure today to introduce Professor Anthony Peirce. And Anthony is a professor in the Department of Mathematics at the University of British Columbia. And he did his PhD as a Fulbright scholar at Princeton University. And he did pioneering work on the optimal control of quantum molecular systems. And prior to his PhD, he worked as an applied mathematician at the Chamber of Mines in South Africa. And there he investigated rock fracture processes. And you can read his contributions, but it's really very impressive, ranging from fundamental mathematics to things that really are practically related in the hydraulic fracturing industry. Many publications and 2 patents. And this is just a very brief introduction, but it's a pleasure to have Professor Peirce speak to us this morning.
Thank you, John, and thank you for inviting me and giving me the opportunity to share some of this work with you. Let me share my screen if I can still manage to do that. Share screen. Can you see that?
Indeed.
And okay, I'm gonna. Is that all visible now?
It's very good.
Okay. Well, first of all, I'd like to acknowledge that this is work in collaboration with Emmanuel, my co-conspirator in all of this. So Emmanuel set the stage at the last ARMA lecture. So he sort of set me up for discussing this sunset solution. Anyway, I won't waste much more time on that. I also want to acknowledge that some of the results in this talk are going to be are a result of a collaboration with Brice Lecampion's group at EPFL, and in particular Andreas Mori, who's one of our participants in this workshop this morning. Anyway, so just as an outline for this talk, I'm going to discuss the model, review some of the tip asymptotics for those people who weren't here last time, and then just discuss the numerical solution. And in fact, this is a case in applied math where the numerical solution led us to notice some sort of phenomenon, which we call a similarity solution, which we wouldn't have otherwise, if we didn't have the numerics, we wouldn't have looked for it. So I'll show you some of the evidence of that. And then basically take you through the story of our hunt for the similarity solution by guessing the functional form, Taylor series, I mean, and some interesting stuff comes out of that. And then what came as a sort of surprise, the functional form of the sunset solution is actually very simple. And something that came out of the review process was we actually figured that this solution could actually be useful to try and estimate the Likov coefficient. And though we did our results for a plane strain, a radial fracture, we also have discovered that this thing is actually quite ubiquitous. It occurs even for fractures that have a history of actually undergoing quite big symmetry breaking geometric changes. Okay, so this is a diagram that Emmanuel actually put up. I'm just going to, I've sort of adopted it. There are basically 4 phases in the life of a hydraulic fracture. There's propagation before arrest, the arrest point T sub S, the shut-in point T sub S is denoted by a black line, and we'll sort of adopt the color code that black will be for the sort of post shut-in solution. And then the green line is the arrest point, and where the velocity is 0, and we're trying to find the stress intensity factor. And then the fracture decides to start receding at T sub R, and then ultimately it collapses at T sub C. And Emmanuel talked at length about these things, but today we're going to be talking about the emergence of the sunset solution, which happens here at the end, towards the end of the life of the fracture. Okay. And now diving in, I'm unfortunately, I'm in a math department, so we can't get away from the math. So I've chosen to write down the equations in this moving coordinate system, because this is what we use, and I think Jaeger was one of the big proponents of this. This moving coordinate system is very useful for modeling, numerical modeling of these simple geometric problems. The analysis includes the KGD, where this is a plane strain fracture stretching off to plus and minus infinity. This is just a cross section. Or when that's when delta is 1, or when delta equals 2, we have a slightly different kernel, and you're basically rotating this around the well bore. Okay, so R is going to be the fracture length or the radius, whichever way we talk about. The lubrication equation assumes this form, and delta is one of these two parameters. And we're going to model our leak off in this situation on Carter leak off. But the analysis that we perform actually is independent of really what type of leak off you're dealing with. It just can't be singular. And we assume it's just a function of time. And then the normal propagation condition has to be adjusted to include the stress intensity factor, which is shown on the left here, dropping below the fracture toughness. The velocity is 0, and then basically when the stress intensity factor is 0, the fracture will start moving backwards. I must say that the whole talk is centered around the problem when there is leak off. Okay, Emmanuel talked about the impermeable case, but that's not really as interesting as the case with leak off. Okay, I just wanted to talk a little bit more about the behavior of G, because this is actually fundamental to our analysis. So in this top plot where I've plotted with this heading time variation, I've plotted the leak-off coefficient for the propagation after shut-in, the arrest phase during, when the fracture is stationary and deflating, and then when it's receding. And this is plotted as a function of the distance, where T minus TC is the collapse time. Okay, so basically we're moving backwards to the collapse time. Okay, so you can see the leak-off is very singular, and this is in the tip element, and then it gets much less singular and then almost becomes a constant as a function of time. And here I've looked at the spatial variation. This is the at the point of shut-in. This is what the leak-off in the very tip element is, and this is plotting it backwards from the tip backwards to the wellbore. So you can see it has a huge variation. And then this is during arrest, and this is that's at the initiation of arrest, and this is the initiation of recession. So basically, we assume that this is not a function of space; it's just a time varying function. And basically, as after propagation, we're not breaking new rock. So basically, T naught has an upper bound, and T minus T naught keeps increasing because time goes on, and it becomes less and less relevant. And this happens particularly when the fracture is going backwards, because now you're recovering new ground or old ground, which was where the trigger times were close to the very inception of the fracture. So this T naught becomes irrelevant, and the leak-off coefficient just becomes a function of time. And that's what we're going to be assuming in our analysis. So this is basically a one-slide recap of Emmanuel's talk. Basically, this is the semi-infinite fracture. We're thinking of this, Emmanuel coined the phrase, the tip umbrella, asymptotic umbrella, where all these multi-scale processes are happening which dominate the behavior of the hydraulic fracture. And Emmanuel and his school, I would say, have championed the analysis of this asymptotic umbrella. And it really stretches from what we call the tip to the boundary of the channel. And that boundary of the channel is what we denote by infinity. So the channel is where sort of boring stuff is going on in the fracture. And this is where all the action is. So these semi-infinite fracture equations can be reduced to this non-singular, non-linear integral equation, which makes it particularly amenable to analysis. And this is something that Jaeger and I guess, this inversion formula was actually due to Dimitri and Emmanuel, and then this non-singular formulation, basically Jaeger and I were involved with. So let's just think of the very point at which the fracture stopped, and basically the square root asymptote that we all know dominates the tip umbrella. But then, as the stress intensity factor drops, so the region, the length scale on which that square root is active becomes much smaller. And if you're a numerical modeler, say your mesh size was like this, when stretched as far as this point, then it would be inaccurate to say that it was all occupied by a square root. So you actually have to account, unless you have a numerical model that actually is on this sort of length scale, you're not going to account for, you won't get an accurate estimate of the stress intensity factor if you say had a tip element that was on this length scale. So for that, if you wanted to use larger elements, you need to account for this multiscale asymptotics. And we identified this G or 3/4 asymptote, which starts to encroach on the square root asymptote. And basically, as you move away from the tip, the fracture goes from square root down to the 3/4. And then ultimately, as the stress intensity factor drops, it goes to 0. When it's actually 0, then the 3/4 occupies the tip. And this only happens, this is ephemeral. It only happens for a split second, and then it's gone. And then immediately the recession, the fracture's moved into recession mode. And as the velocity increases, this recession starts to encroach upon the 3/4 asymptote. So now we're going from the tip, where there's the recession asymptote, which is a linear function, and at the channel region, the 3/4 being driven out, and then ultimately you just get the whole tip umbrella dominated by this linear asymptote. So that was basically Emmanuel's talk from the previous time. I mean, I've just sort of given a sketch of what happened. Okay, so armed with this linear tip asymptote and the ability to transition, if you went straight from stress intensity factor to the linear asymptote, we found there was a big jump in the solution as you went from arrest to recession. So you need to go through all those multi-scale asymptotics to get a smooth transition. But armed with that, we then were able to get what we believe was a fairly good numerical solution. Now it's black, so the thing is still propagating post shut-in. That's the point of shut-in. And now suddenly it arrests, and now the green line shows the initiation of arrest, and the blue line is showing where the fracture starts to recede. And you'll see there I've identified two sort of instances of this fracture where they fracture profile. By the way, this is the width and this is the pressure, but two instances of this width profile that look very similar. So, I mean, and I'm talking about similar in a geometric sense, where, you know, if you have similar figures, you can scale the lengths of them and they'll fit on top of one another. Well, so the question was, are these self-similar solutions? Can we rescale the one to fit on top of the other? So I'm going to basically replay the same data. I'm going to ignore the pressure for the moment. And I'm going to, this is the efficiency and the wellbore pressure. And I'm going to replace this with two other graphs. And we're going to, I'm going to replace the width with the scaled width. Okay, so it's the same data, and I'm only going to look from the recession backwards, okay, or recession onwards. And so that's the arrest point. This is the shut-in point, and this is the arrest, the recession profile at the beginning. So what we've done here is we've taken the width of the wellbore here, and at each time step, we've divided the width in the fracture by the width of the wellbore. Okay, so W of R of T divided by W, and that's what's plotted on the y-axis. And on the x-axis, we rescale the R coordinate by the total radius. So basically, even though this goes up to like 270 meters, it's actually now going to be 1 for all these fractures. So that's the sense in which this is rescaled. So we're rescaling the sides, if you like, of the solution. And the rescaling factors are going to be plotted here. And the width as a function of time at the wellbore is plotted here. So now we're going to plot the evolution. And now we can see that as time progresses, the fracture actually starts taking on this universal form. Okay, there's this function big W. Okay, so essentially you can see here it's tended to this universal form, and it happened fairly quickly. And the scaling factors that we need are, this is on a log scale, this is a power law, and this scaling factor is also a power law. I mean, this is a linear graph, so this is actually a straight line. So this is actually, we suspect alpha is equal to 1. Okay, so taking that forward, on the top here, I'm going to get in the habit of taking information from previous slides and putting them at the top. So from the numerical evidence, we get this. These are the scale factors, they power laws, and we've got this universal function. So we guess a solution. Okay, we're looking for the similarity solution. So we guess a solution that looks like this. So there we're replacing W of 0 by T to the alpha. The pressure has another power law, and the radius looks like this, T to the gamma. Okay, where S is R over T, that scaled coordinate. And that was the one I introduced at the very beginning. And T prime is the distance, the difference between the final time of collapse and the current time. Okay, so this is actually we're moving backwards in time. I mean, if you like, in this T coordinate. Okay. So some quantities that we can calculate given this universal function. So we just integrate and take the average width, and we can rewrite it in terms of these variables like this. And W bar is the average width of this universal function. We can calculate the volume. Basically, it's pi r squared times the average width gives you the volume. And that has this manifestation. The volume change is basically the derivative of this thing, okay, which was manifested here. And the volume change is equated to the amount of leak-off, the leak-off velocity times pi r squared again. And that ends up looking like this. So if we equate these two, we can see that the gamma delta terms cancel, and we can see that there's no other t on the right here, no other power. So alpha has to be equal to 1, which is exactly what we got. And we can also solve for W bar. Okay, so now we want to see what functional form we get for this this universal red line, this dashed red line, which I call W of S. So it's convenient to write it in terms of a tip coordinate by doing this transformation. S hat equals 1 minus S. So S hat starts off at 0 at the tip and moves back to 1 at the well bore. Okay, so, and all I do is okay, so we've got T because alpha was equal to 1, T prime there. And so now we're just looking for the functional form of this. So I just do a Taylor expansion. And why is it? Okay, so we know that the width at the well bore at the tip is 0. So that's 0. And we know because we had this linear asymptote, we know that we can use a Taylor series. If it was some other power law, we'd have to use a Frobenius series. But yeah, the common garden Taylor series is fine. Okay, and so we assume this form for W of S, where I've just introduced the notation W sub n is the nth derivative at S equals 1. Okay, so this is back to first year calculus, if you like. Now we go back to the lubrication equation. Okay, and we're going to plug that series solution back into the equation. Okay, but now we need the equation written in tip coordinates. Okay, so we use S hat equals 1 minus S, and the equation boils down like this. So I've expanded these two terms for the pressure. I've differentiated with respect to S. And yeah, anyway, this term actually ends up being subdominant to this one. This is the important one. Okay, so anyway, this is the full lubrication equation, and G naught is assumed to be just a function of time. Okay, and we have that series ansatz that we have, and we plug it in. And if we collect the kinematic terms, we can write it in a convenient form like this. Now comes the sort of more involved part, I guess. So we've got this far, we've got the width, we don't know what the pressure looks like, and that's what we're going after now. And R equals this lambda T to the gamma. Okay, so we go back now to the elasticity equation. This is just a little bit like numerical modeling. We've got these coupled equations. Sorry, let me just go back to this. Sorry, I'm having trouble with this mouse. Anyway, the elasticity equation, if you do an expansion around the receiving point, it has both those both the radial and the KGD fracture have this form, which boils down to, if you transform back to the distance between S and rho, it boils down to this. So basically the dominant behavior of the elasticity equation looks like this. And we use this identity. Now, if we look here, we're going to have to calculate powers of, integer powers of S hat. So this integral here, because we have derivatives of W, we're going to have to use the integral powers of S hat. And it boils down giving you rho to that same integer power times log of rho. So if you go through the algebra, you can write down an expression for the pressure in terms of this rho to some power times log of rho. And out of this pops, if we look here, 1 minus gamma is what the pressure is, and the pressure was T to the beta. So now we've captured beta. It's 1 minus gamma. And if we proceed and we plug in the width cubed and differentiate, we can extract the dominant behavior, the leading behavior of this. And lo and behold, it looks like this power law times s squared times log. So these terms are all regular. Okay, but something more interesting happens. So the typical term of all of this series looked like this. Okay, and if gamma is less than 1, then t prime to the 4 minus 3 gamma is bigger than, 4 minus 3 gamma is bigger than 1. So that means you've got t to a positive power. Okay, and as t goes to 0, that's going to go to 0. So that means there's basically all the pressure gradient terms are going to vanish as t goes to 0. And why do I say that gamma should be less than 1? Well, as the fractures receding, so the width is going down, and the width gradient is decreasing, and to match a constant g, the velocity must be increasing in magnitude. So it's accelerating. So in order, if you look at r dot, okay, just differentiating this power here, if you look at r dot, it gives you gamma minus 1. So if this is to increase as t goes to 0, gamma has to be less than 1. Okay, gamma can't. So ultimately, basically, that means that the pressure terms become irrelevant. Okay, so now we go back to the lubrication equation. And I can basically, because of that logic, we can throw away these two terms. And this is really quite profound, because basically it says that kinematics is decoupled from dynamics. So there's nothing involving the modulus, the elastic modulus, Poisson's ratio, or the viscosity in the dynamics from then on. Okay, or I mean in the kinematics from then on. So you get this simple kinematic condition, which is local. So how do we interpret this? So at the fractures reach the state where essentially there's fluid trapped in the fracture. There's no pressure gradient to move the fluid around. So the fluid's just leaking off in situ. And this term here basically is governing how the fracture recedes due to the fact that the leak off in the tip, the width in the tip is smaller. So the leak off is going to cause the fracture to basically shut down there and then move backwards. So that ultimately the dynamics becomes very, very simple. Okay, and if we look at the kinematic term, when I say dynamics, the evolution of the fracture becomes very simple after that. So equating the kinematics term to this, plugging in that series solution, we match powers. So this term equals G naught, okay, which gives us that. And there's no other power in S on the right-hand side, so the coefficient must be 0. So we get this little recursion. And ultimately, we end up with that series solution. Okay, so that's where we get to now. So we start with a power series solution. And just to recap, we ultimately looking, W of S is G naught times the square bracket here. Okay, so what we've got is now a solution for this. But I mean, for a mathematician, there's some anxiety here, because as S goes to 1, this series doesn't converge. Because we've got we got this factorial in the basement, but we've also got a factorial essentially in the numerator. So if you do a test, basically the series won't converge at S hat equals 1. But all is not lost, because if you take a look at the series, you can see that basically if you have gamma being a reciprocal of an integer, like gamma equals a half, then this term appears in all other terms. So basically the series terminates and you get a polynomial. So this is what happens. And I mean, you know, you think, gosh, we've got now not one solution, but a countable infinity of solutions. But there are precedents for this. I don't know if any of you have taken a quantum mechanics class, but if you have the harmonic oscillator, quantum model of the harmonic oscillator of a diatom, you end up with the Hermite polynomials by just exactly the same truncation of series. So we can call these the sunset polynomials, if you like, but you end up with polynomial solutions, and they assume a pretty simple form, this basically nth power. So just observations about it is the width is positive, means that you can't, n must be even, because we can't have negative widths. If we take the derivative, differentiate with respect to s here, you're going to basically, you get ns to the n minus 1, and at s hat equals 1, which is at the well bore, it's 0. So basically you got a symmetry condition, and for the higher powers, all the derivatives up to n minus 1 vanish at the well bore. So it's very flat. Okay, and at the tip, the tip gradient increases with n. And ultimately, we'll see that the solution that really is the most important one is the case when n equals 2. Okay, and this is what we call the sunset solution. So it has this embarrassingly simple form. It's just a quadratic, a parabola. These are the scale coordinates. When n equals 2, gamma's a half. So that gives us that. We can extract the pressure explicitly for the KGD case and at the well bore for the radial case. So estimating CL from the well bore aperture using the sunset solution. So imagine a thought experiment where we could measure the rate of decay of the width. So that means basically taking dw dt here. That's going to give us G naught times 1 minus S. So if we had it at the well bore, S equals 0. S is not the tip coordinate, the real coordinate. So S is equal to 0. So dw ds is just going to, dw dt prime is just going to give us G naught. By the way, we could measure it at any other point and we'd still get, if we took the rate of decay, we'd still get G naught. That's pure and simple. Back to the asymptotics of G. Remember, as T goes to TC, this is over a long time of the evolution of the fracture, T naught becomes irrelevant and G naught looks like this. And this is the secret. Basically, we can get C prime, but if we knew G naught and we know what the time is, we can get an estimate for C. And that's it. Okay, and this is assuming Carter leak-off, but I'm sure you could do it for other types of leak-off. But all we've done is assume that the leak-off function is a function of time. If we had a trace of the pressure, then we could also get an estimate of the collapsing radius. Okay, so here's a graph where I'm actually going to plot the case n equals 2, 4, and 6. And in this little window here, I'm going to basically measure the time derivative of W as a function. Just taking a forward difference as the fracture moves back towards the collapse time. Okay, so let's look at the video. By the way, C prime for the simulation was 4.35 times 10 to the minus 7. So it's not too bad an estimate that we get from that. Okay, so you can see, first of all, we observe that basically the higher powers don't cut it, whereas the solution tends to the n equals 2 case. So what we call we call n equals 2 an attractor, and we're getting pretty good estimates of C prime. Okay, so now I promised to show you some results from, we have a collaboration with Brice Le Campion's group at EPFL. They have this PyFrac code, which is an ILSA model written in Python. And basically they have a width constraint. And we've been looking at what restrictions we need to put on WC in order to be able to model recession accurately. Okay, and it is possible, but that's forthcoming. It will be published fairly shortly. So what I'm going to do is to show that, in fact, even if the fracture undergoes some symmetry breaking excursions into layers and stuff, when it comes back home, like salmon, when it comes back home, it gets back to this sunset solution. Okay, and the movies and the simulations are thanks to Andreas Muri, who's one of our participants today. Okay, all right, so one note is that basically the recession asymptote still applies, but we've got, instead of taking W equals this, we've got to take W minus WC. So if we have a width constraint, on top of that layer of width constraint, there's still this recession happening where you're getting this decoupling of the dynamics from the kinematics. Okay. All right, so here's a view graph that Andreas prepared. The green, so this is a case where there's a homogeneous Leakov coefficient, and there are basically the green zones have an intermediate stress, the blue zones have a higher stress, and then there's a stress drop to 4.75 GPa in the red zone. Okay, and here's the evolution of the fracture. So you can see it's undergoing a significant sort of geometric changes, and lo and behold, the sunset solution still seems to prevail close to the end. Okay, and you still get this linear power behavior, and basically it ends up as an ellipse, and the semi-axes also have this square root behavior. Right, so this seems quite this decoupling of kinematics and dynamics seems quite fundamental. Okay, just as a note, Andreas estimated the Leakov coefficient in this region, and you notice there was another region here. So here it was, the actual Leakov coefficient was 2 times 10 to the minus 6, and the estimated one was 2.11 times 10 to the minus 6. So the top patch, it was slightly worse, but still you get not too bad an estimate. So even if it's more complicated, we have a heterogeneous CL. So here, basically CL in the green zones is 2, and in the stress jumps are the same. It's 2 times 10 to the minus 8 in the blue zones, so it's very little Leakov here, and then a lot of Leakov in the red zone. Okay, so so the green zones have intermediate Leakov, if you like. So here's the movie here. I mean, compared to this, it makes my videos look like home 8mm home videos. Anyway, and you can see the sunset solution still prevails, even though the fracture's undergone this very complex history. And here, the estimate is 2.06 times 10 minus 6 at the injection point. Okay, so some conclusions. So hopefully I've managed to convince you that there's this emergence of a similarity solution close to collapse. I took you through the construction, and I mean, I apologize if it was a bit too much math. But anyway, the construction of the sunset solution, but it was based on the numerical evidence that we had the functional forms that we could look for, etc. And most important was this R asymptote, which gave us the idea that we need a Taylor series. Interestingly enough, we can get fairly good estimates of the leak-off coefficient from the aperture decline. The sunset also, it's quite ubiquitous, even with complex geometries. So I think I mean, the results of this sort of give us an opportunity. I mean, we've got potentially a new way of measuring the leak-off coefficient. But the challenge to you now is to go out and measure it. How are we going to find ways to measure the aperture decline? I know there was a talk last year about the aperture decline, but I'm not sure whether those results would have been. I mean, maybe they can try and see if it would work. Anyway, thanks very much for your time.
Thank you, Anthony. Very provocative. And we do have some remarks from Mark McClure.
John, this is Ali Donishi. Before we go to that, I've got a fundamental question just for clarification. Is this model assuming that during closure, the fracture tip recedes towards the wellbore as opposed to fracture elastically and uniformly closing, reducing its width during the closure time? Can you please help me understand which model you're using?
Oh, so the fractures, I mean, it's not uniformly closing. I mean, the elasticity is all included in the coupled equations, right? Is that what you?
No, what I'm saying is the fracture, the tip of the fracture doesn't move back, doesn't recede. The fracture doesn't get shorter. It just simply gradually reduces in its width. And the reason for that kind of a model is that during closure, very shortly after the fracture job is finished, a couple of days maybe after that, the pressure equalizes inside the fracture. And if the pressure equalizes inside the fracture, then its closure will be uniformly decreasing in width, proportional to the actual width.
The tip is because of leak off, the tip is receding. It doesn't stay where it was.
Okay, I understand your model now. Just for reference point, I don't think that's what happens. I think the tip of the fracture stays where it was. Once the rock is broken, it's broken.
No, but there's numerical evidence that shows that it actually goes backwards. I mean, there's lab experiments that show that it goes backwards, it recedes.
Okay, let's agree that we disagree on that model. But thank you very much.
Okay.
Go ahead, please.
Well, so you might have some additional disagreements.
Actually, can I stop sharing? I guess then I can.
Oh, absolutely.
Yeah.
So, and then you can look at the chat as well. So Ahmad Ghassemi had some similar comments, and Ahmad, I don't know whether you want to.
Yeah, so I guess some of the experiments that Hameson did many years ago indicated there were two stages of closure: a hinge type closure and then a zipper type. So one needs to distinguish those two.
This is definitely the zipper.
Right.
Yeah.
Yeah,
I mean, the hinge type closure. I mean, basically, that's when you don't have leak off. I mean, that's the so-called Stephenson condition. And in fact, Emmanuel and I managed to use the tip asymptotics to prove that that's the case. Basically, the fracture cannot, I mean, the geophysicists sort of reason the fracture cannot, you can't squeeze out, you'd require an infinite amount of energy to squeeze the fluid out of the fracture. But if there's leak off, it's going to be a zipper.
Okay. So two other comments or questions, or a combination thereof. One is the stress intensity factor that you're using, that still is applicable for a joint or a natural fracture closing, essentially, because that's what we have, right? Now you have a surface that is rough, so the definition of SIF should change probably.
yeah, but this is when it's closing in situ, right? I mean, yeah. I mean, the thing is the results that we're talking about, even if there's joints, I mean, we could think of the joints as being some sort of width constraint. If you say that the average value of that is a constant, then essentially this is going on top of that. There's this upper layer, and this recession is of the fluid that's still trapped in the fracture. And when you get this decoupling of the dynamics, I mean, the Young's modulus, all of that goes out the window. What type of fluid? It's just the fracture, the leak off. The fluid is just going down, and that's the opportunity to possibly measure this leak-off coefficient.
All right, so that's what you mean when you say the dynamic drops out, all the rock aspects.
All the rock properties and in fact the viscosity is gone, right? From the equations.
Thank you.
Yeah, I mean it's obviously a fundamental decoupling. Yeah.
I agree with you that the closure of the fracture occurs because of leak-off. Without leak-off, the fracture will not close. And at that point, I'm completely in agreement with you.
Yeah.
The discrepancy between our two opinions is whether the leak-off which is causing the fracture to close, causes the pressure along the fracture to change. Because as long as the fracture is under a pressure which is above the minimum principal stress, it is open.
Oh yeah, the fracture is still open. We saw the
entire fracture is open.
Yeah,
the fluid pressure inside the fracture, inside the entire fracture is above the minimum principal stress. The fracture is open and it closes gradually as leak off takes the fluid away from inside.
Yeah, but that's not. We're not. I think. I mean, I didn't emphasize the pressure, but you saw the pressure there in the very first video we showed. We tracking the pressure, and yeah, it is open, but then it starts to zip closed, right?
Just one more question.
Well, let's. Ahmad, I'll come back. Ahmad, I'll come back to you because Mark has had his hand up, and I know Mark's comment is going to be related, and it's related to the width constraint that closure may not be complete. And Mark, do you want to elaborate?
Yeah, sure, because I do think it is relevant. So thanks for the talk, Anthony. So when the fracture is closed in your mathematical model, does leak off stop at that location?
When it's closed, yes. Yeah.
So that's the key thing.
Yeah, but
that I think
I mean, basically, I don't think. I mean, I think that what you're talking about is you spoke last time about like a joint, when you put springs in and the like. When you model closure, if we assume that say as a first approximation the closure is some sort of constant, the leak off can continue from those other fractures, and this process will go on over and above this. I mean, it's what we're talking about. I mean, and that showed up in Andreas's results. Basically, the width, he had a width constraint. Yeah, he didn't have any leak off from the elements outside. But if you're leaking fluid to those elements outside, all it's going to do is it's going to change the time scale. But the collapse of this in situ collapse of this fracture is going to still continue.
Okay, well, maybe so. I mean, that seems possible, but I get, because there is, what I would question is the scaling with time. So if the leak off area is decreasing with time, that's going to result in a different closure scaling with time than if the leak off area is constant.
So
you have an equation, right? You have an equation for the radius of recession versus time. But it wouldn't just scale linearly, it would scale non-linear. I mean, it would be a different function, right?
Yeah, but I suspect that on top of that, we'll still get this closure. I mean, we'll still get the sunset solution, because I mean, it's a fundamental decoupling of the two, right?
Okay, well, that would be interesting to look at, because I mean, the way I think about it is leak off continues everywhere, and then also the walls contact at a finite aperture. So those two things I don't know,
Yes.
maybe they don't change your solution. I don't know, but it seems like those are important considerations because,
Yeah.
if you wanted to do a calculation that encompasses everything. So the traditional way a frac simulation is run is that leak off ends when the walls are in contact. That's what most frac simulators have done for many years. But that means they can't simulate the whole pressure transient because once the cracks close, the simulation is over, right? But reality doesn't stop, right? And we continue to see leak off and the ongoing pressure transient after all of that. So that's the fundamental problem with classical fracture simulation of closure. And so,
but
anyway,
I mean, not all frac simulators assume that. I mean, there is leak off from, and I mean, it gets kind of complicated because you get these little islands forming and you've got to shut those down as well, right? So,
okay. Well, anyway, it'd be cool if you included that and
yeah.
see how that.
Yeah.
Cool. Thanks.
Yeah, I mean, that's these questions. It'll be interesting to see if we still get that solution. It might be, it might just change the time scale.
You need to know the rate. Okay, and the other thing is it'd be interesting to compare that with like pre-closure and post-closure estimates of leak off. So like I've compared pre-closure and post-closure estimates from field data, and I had like a paper where we looked at like 62 of them, and they were always within a factor of 3. And so it'd be cool to maybe compare those estimates with this method and see if you're getting a consistent answer.
Yeah, actually, one of the big things is what width do you assume? Because that can make a big impact on what's happening, right?
Well, that's why we've traditionally used post and pre-closure, because the closure part is viewed as the most difficult to understand. Yeah. So before closure, we don't need to worry about roughness, and at late time, we don't need to worry about roughness. We need an area estimate, but otherwise we're avoiding this very challenging thing in the middle, which is what you're headed for.
Yeah, I mean, well, you've got to hit it head on, right? I mean, the thing is, this might shine a light on that, right?
Yep. Okay. Thanks.
So I know Professor Gassimi's arm is getting sore from having his hand up.
I dropped my hand. No comment anymore. No, excellent analysis. I was just maybe I'll make this comment and for clarity's sake. So, do we still need a leak-off coefficient, or can we, recast this analysis in terms of, say, a formation permeability, move towards, say, a poroelastic formulation? I mean, that would be really great, I think.
Yeah, I mean, I think you can, the estimating G0 can be used to go back and find parameters in any model that you might have of leak off, right? I guess that's it. Is that answer?
Yes, yes, yeah.
I mean, I think that's absolutely true. I mean, Emmanuel's the expert on poroelasticity, so he could probably also weigh in there, but yeah.
Thank you.
Ollie, do you have any other observations?
No, the entire computations and the equations and everything really is heavily dependent on what mode of fracture closure is occurring. And as long as we have got a difference of opinion on that, then that dominates the conversation.
Yeah,
but I are you saying that all the fractures that, I mean, you're assuming that everything is what Professor Gassami mentioned was a hinged fracture?
Yeah, I'm in my way of thinking, the fracture during the closure, the length of the fracture doesn't change. It's the width of it that changes, and mainly due to leak off.
But I mean, the experimental evidence doesn't agree with that, because I think Hans de Pater showed that in lab experiments that you do in fact get recession of the fracture.
There are both tend to occur.
Exactly. And I think it depends on it'll largely depend on whether leak off is a dominant process. If there's very little leak off, you might just get the hinging, right?
And I was speaking to Steve Hickman. He mentioned some experiments they have done, and they see the closure at the wellbore first.
Yeah. Well, that's another ball game, right?
Yeah.
So, anyone else want? Emmanuel, do you want to make an observation?
Yeah, just want to chime in and respond to Ali. Ali, the first part of the closure takes place exactly as you said. No, the fracture is arrested. The fracture is deflating. So that phase is absolutely completely consistent to what you said. But at one stage, K1 becomes equal to 0. And that the only thing the fracture can do then, if there's leak off, is to recede. No, there's no other way. But I mean, the first phase is indeed a case where the fracture length remains constant.
Correct, but that occurs very, very late in the life of the fracture.
It all depends on leak off, and there could be phase where you have very long arrest time compared to the recession time, or it could be different. It just depends, no, on the parameters. But in any case, what I think what the solution tells us is that at the very, very late stage, no, if you can capture that, then you can have an insight on one of the parameters, no, as Anthony explained.
John, I have a question. Maybe it's just semantics, but I'm a little confused. But to me, it seems that when you create a fracture in your substance with the rock or the material, that unless that substance is self-healing, that fracture is there forever. And so the width changes, but the fracture doesn't go back and forth. I don't understand that, but maybe it's just in semantics when you're talking about that.
Yeah, and I feel the same way as you did, yeah.
But see, once that fracture is there, it doesn't disappear unless your substance is self-healing. And so once it occurs, it's always there. But
I mean, it can close, and even if it closes to a finite value, the solution still carries on, right?
Yeah, it can close, but you don't ever change this so-called stress intensity factor because the rock has come apart. And so that fracture is there unless it's self-healing in some way. So certainly the fracture closes, and it can close irregularly, as been mentioned before, as it undoubtedly does in rocks, at least in some cases.
But isn't there, I mean, the stress, if it's broken ahead of it, the stress intensity factor is going to be 0, right?
Yeah, right, and it doesn't ever change. I mean, it's I guess 0 unless it's self-healing.
But the stress intensity factor is a function of the width, and as the width goes down, I
don't think so, because once the fracture is there, you don't have a stress intensity factor anymore.
No, that's
it's simply as a matter of
right. Well, but I mean, the stress intensity factor is looking at potential growth, right? Because it gets to the boundary. And this is the phase in which Emmanuel was talking about, when that green phase, when it's arrested, the stress intensity factor drops as the width goes down, right?
Well, it does, but I visualize the stress intensity factor being right at the crack tip.
Exactly. That's where the stress intensity factor matters, at the fracture tip.
And it's the tip is the separation point between the virgin material that hasn't broken or come apart and the material that has come apart. To me, that's the crack tip, and that doesn't change once the rock comes apart at some location, unless it, I keep saying, unless it reheals itself.
But to have a stress intensity factor, you have to have a width that's a square root.
Well, you have, I think, a stress intensity factor is certainly a function of the width and the material itself, whatever it is. Form that intensity factor, I guess, whatever that means in rocks that are linear. But to me, it doesn't go back and forth, because once the fracture occurs, that rock is broken. And so there is no intensity factor at that element anymore, I don't think.
I think that's what's being indicated here, Sid. And maybe
And then the fracture goes backwards.
Yeah, and I think I would encourage you and Anthony to discuss those semantics offline, because indeed the stress intensity factor is a function of geometry, the internal pressure, and the width. And
John, I think that it's really a point of semantics, because I think that indeed there is the fracture tip, the point at which the rock is unbroken, and that as the fracture recedes does not change, of course. But I think what Anthony is dealing with is the point of closure, the point at which the fracture is closing, and at that point, what we can define a stress intensity factor, and that at that point the stress intensity factor is equal to 0. So it's a point of closure. So I think that we have a discussion on semantics.
okay, well, Emmanuel, Emmanuel gets to have the last word in this case.
Sorry.
Hey, what a fantastic discussion. Really tremendous participation and a fantastic presentation. So I'd like to thank you, Anthony, tremendously. I really enjoyed this, and thank you.
No, thanks for your attention.
Very nice to both Anthony, you and Emmanuel last time too. Thank you.
Thanks, everyone.
Bye.